Well, hello and welcome back after we're post spring break here. Ooh, hang on. Hello and welcome back to the game. Whoa, dang it. Okay, there we go. My goal is by the end of this semester to remember to close down the audio feedback, so it doesn't do that where I start talking into the mic and then I've got myself up on a monitor so I can see kind of the lag of stuff coming through YouTube, the space between when I write it and when it shows up on the screen. And but because of this, because there's a lag, I'll start talking and I forget to mute my computer monitors, and then it's like I hear myself saying hello, and then I mute it. My goal is by the end of the semester to remember that, so I maybe can get one video off here without surprising myself and being like, oh, mute. So I hope you're having a good morning. We're still in the morning time. It's we're just kicking it. Lecture starts at 11:30, but I just wanted to log in, say hey, see what's up. Definitely did not. I definitely did not have the excuse me, spring break that that I envisioned that I'd have at the beginning of the semester. Normally I don't have spring break plans. Normally my spring break plans are I don't go to work for a week. Oh, whoa, sorry. I just kicked my desk. Nuts. This spring break, I actually had plans, which was weird. So this spring break, I had plans. So I went to I'm a Southern Californian, born and raised. That's why I say totally every other word. But I went to community college out here, or down there, college down there. I went to UC Irvine, but then I went to NYU for grad school. So I was on the East Coast. I was in New York. Very different experience. I loved it. And this spring break, my wife and I actually had plans. Our plans were our kids have never been to the East Coast, and our youngest is just at the age where we don't have to buy him a plane ticket yet. So we had bought tickets to fly out there. She was born in Pennsylvania, so that we have friends, family to stay with, and I was going to show him the city. And New York. My 11-year-old daughter, super into musicals. She was going to see a musical called Dear Evan Hansen on. Yeah, totally. It was right on Broadway. I was gonna get a tattoo from my tattoo artist back there, whom I haven't seen for like 6 years now. I haven't been back since I graduated in 2014. So we were pumped for it, and then COVID happened. So we didn't go to New York. We stayed at home, and we're still planning on taking the trip sometime. But instead we're staying at home. So what did I do instead? Well, I sprained my ankle. I rolled it because I wiped out on my one wheel on Monday. So I rolled my ankle the first day of spring break, which maybe that was a sign that I should have been indoors grading, because that's how I ended up spending the rest of it. So hopefully your spring break was better than a canceled New York trip and a sprained ankle. But that was mine. The funny thing was my wife also, she So I have a sprained ankle. She was taking care of the baby. Then she threw out her back, and so we were like two gimps. We managed to get through it. We're both doing better. I actually went out for a ride yesterday, and the heel was sore and like tense, but still functional. It was good to ride again. Yeah. Hey, happy Easter to you. One day late, Salvish. Oh, one wheel like a unicycle? Oh man, hang on. Here. Hang on. Yeah, it's like yeah, here. It's a one wheel is a well, here I'm about to show you. Skip ad. Here. A picture's worth 1,000 words. It feels like I don't know, like snowboarding or something, but on pavement. Yeah. I'm totally talking about Salvage. I'm totally talking about the electric one wheel skateboard thing. Yeah. That is exactly it. Okay, so recapping right now, our where are we? Oh, sorry. So the exam grades are up, and I will be. I have not yet emailed them to you, so I'll be returning those to you by email, the graded version. So you'll get it back just like you. You are so right, Salvesh. You'll be getting them back just like you would have if you had taken it in lecture. And the reason why those emails haven't gone out yet is I'd been focusing so much attention on our exams and writing it, getting it graded, that I had fallen woefully behind for my lab class. So I finished grading our lecture, and then I moved on to grading my lab class lab reports, and I got 3 of those graded. So all the grading's done. I still need to kind of like compile them, send out emails, return stuff. So that will be happening this week. I don't have an exact day planned for it, but I'll be slowly chunking away. One thing I can promise you though is everybody's exam will be returned at the same time, because what I'm going to do is because I don't want it to be unfair. Like the first email I send gets it first. Everyone's going to get it at the same time. I'm going to schedule an email send off in Outlook. So I'm going to make everyone's email, write everyone's email, and then everyone's exams will come back all at once. So you don't need to worry about getting the short end of the stick. Everyone will be getting their tests at the same time. Okay, so a couple points of business. Of business this morning. Business. Hang on. So we've got a couple pieces of business. The first off is so the exams are in. If you are wondering, kind of, because there's 2 exam scores, right? There's the multiple choice and the lecture exam, or not the lectures, the take home written exam. And so if you're wondering, and they're 2 very different averages, 2 very different scores. So if you in your mind are wondering, okay, how do I make sense of these? Like, because you may be looking at one and you're like, oh, I bombed, and you may be looking at the other and I was like, and thinking, okay, well, I did pretty good. So how did I do on exam 2? if you're wondering what your exam 2 average is, each one was worth 60 points, which is half. Each is worth half of what the total exam 2 is worth. My exams are worth 120. If you're wondering what your exam 2 average is, you take your Canvas average plus the take-home average, add them together, divide by 2, and that'll give you kind of a sense for how you did on exam 2 overall. So if you're wondering how do I make sense of each of those individual scores, that's one way to look at it. When I mail the exams back, another reason why it's taking a little while is I'm going to be including kind of like a cover sheet, and I'm going to have on that cover sheet your written exam average, your Canvas average, and then the combined kind of averages of the two to give everyone a sense. But if you're wondering what that is or how to feel about the exam, you can do this on your own as well, or you can wait for my email. I'll be doing that for you in my response. In addition, so there's a first piece of business. Second piece of business is I desperately need your feedback. There is a feedback quiz in Canvas worth 0 points. And it's questions that I've been wondering about, how effective class is, what your experience has been in class, how you use the tools that I've been making available. I've got questions about like, do you like watching live? I know 15 of you do. Do you prefer to watch later? Do you rewatch if you watch live or later? All that kind of stuff. And also, I really need your written comments. I want to know what I'm doing. What about what I'm doing is working for you? What is it about what I'm doing that isn't working for you? What would be helpful, useful? Again, I'm not married to this format per se. I think it has some advantages, but there could be room to shake things up, to change things. And I want to hear from you because I want to know how I'm meeting your needs well, and then where I'm not meeting your needs quite as well, so that I can try to make that better. So if you could take that quiz and not just rate the multiple choice stuff, but also leave written comments, that's going to be the most valuable feedback for me, is hearing your voice. And as I said, it's worth 0 points, but everyone who does it, I'm going to boost your exam 2 scores by 12 points, which is 10%. So by filling out this quiz, you literally get to jump a letter grade on exam 2. Let's see. Feedback quiz didn't take too long. Took me 22 minutes. It was the same. Okay, awesome. Hatcher, thank you for your input. So yeah, it's not too terribly long. I think there's like 23 questions. So like, if you're thinking about a minute on each question and then answering, should get you through in about that time. Raj, when are you going to add the quiz points? I will be adding the quiz points when the quiz closes. So something to keep in mind is, or I'm gonna switch up my color. This quiz closes Friday, which is, I believe, the 17th. Yeah. So once the quiz closes, then I'm going to go through and look at who all has taken the quiz, and then I'll be assigning the points, because if I do it while things are partially done, then I have to keep track and remember, did I give Raj the points already? Did I not? I'm sure you guys wouldn't mind me losing track and giving more points than promised, but that's what I'm going to do. So I will Add the points after the quiz closes. Totally. So that feedback will be very, very valuable to me. And again, this whole process is in a constant state of evolution. So I want to, I want to keep what's good and fix what's less than ideal. So anyways, that's why that is there. I feel like I'm missing something. We got the exam 2, we got the feedback. Well, yes, Jesse, this is the feedback quiz that I am talking about. Correct. Totally, because it's going to shape the course, but also as I evaluate kind of how exam 2 went. You guys did really well on exam 2, by the way, with both sides considered. I know everybody kind of had the demoralizing blow of the Canvas quiz, which I anticipated being the harder of the two because of the time constraints. But then with the written exam coming in and taken together, the average was ballpark. And I think it was a hard exam, especially in the absence of any extra credit available on it. So you all did awesome. I'm super proud to of your effort, of your performance. So well stinking done. I think our last bit of business is our song of the day, which is the Motherlode. The Motherlode by Mastodon. I am not, by any stretch of the imagination, a metalhead. I've always been more of a punk person, but I really do like stoner metal, and Mastodon is pretty sludgy. So anyways, you can check that out. The link's in the description if you need something a little more aggressive. And this one's actually surprisingly uplifting for metal. So anyways, give that a check out if you're bored. Okay, sorry, we have a question. Kind of random, but since there's no ACS, do we have a cumulative final? Jake, great question. The final absolutely will be cumulative. Absolutely. So yeah, the answer is totally yes. Not the question. Or I guess a question that I still have about the final is what final form will it take? If I were to give a final that is like the ACS, then it would probably be 100% Canvas based. So exam 3, I still need to evaluate, and this is a little ways in the future. Exam 3 will most likely have a Canvas portion and a take-home portion. The final, if I wanted to give the final with an ACS type experience, then it would be, what's the word I'm looking for? Then it would be 100% based on Canvas. I haven't decided whether or not I'm going to do the final all multiple choice, or if I'm going to make the final, what's the word I'm looking for? Or if I'm going to make the final half Canvas, half written. Does that make sense? But regardless of the form the final takes, it will absolutely be cumulative. It'll cover everything from chapters 1 through chapter 11. Totally. Alrighty. So, with that being said, it's good to see everyone. All your smiling profile faces. And actually, everyone's... let's see. How will you grade the ACS section in Canvas? So, quick question, Vraj. Are you asking about... Whoa. Oh, okay. There's an assignment in Canvas called ACS Final. Gotcha. Yes. That is just the final. That is just the final now. I haven't changed the name. So that is just the column for the final exam. Which can't be the ACS final because we are doing remote operations. So there's no way to administer that sealed exam. Yeah, totally. So that's just the final, which is worth 110 points. And the form it takes is to be determined. Totally. All right. I'd actually like to start lecture today answering a question that I received over email about electron configurations involving the F block. So F block electron configurations. All right, and the question here has to do with the question was this: does the electron configuration of a element in the F block, is it affected by the periodic table you use? Because as we know, there is a kind of a warp portal, between in the D block, right? When you look at lanthanum and actinum, lanthanum's 57, actinum's 89, and when you jump one space over in the D block, you jump 14 atomic numbers, right? You go from 57 to 72, you go from 89 to 104, and that's because to move from lanthanum 57, you jump into the F block and go across the F block and come out the other side in the D block. We talked about this last lecture. Now, the periodic table that you use, there are different periodic tables, and the difference in the format really has to do with what two elements are placed here. Lanthanum and actinum are there in the periodic table that I have up here. But if you troll through the internet, you'll notice that sometimes, instead of lanthanum and actinum, sometimes they will be put down with the F block, and the final two elements in the F block are sometimes placed up in the D block where lanthanum and actinum are. And this is totally incorrect. All right. These two, lutetium and lawrencium, are F block elements. All right. These are only F block elements. So this swap is totally wrong. And lanthanum and actinum, these are D block elements. Now, the reason why sometimes lanthanum and actinum are placed, smashed into the F block, is because these two D block elements have a chemical behavior that is very, very similar to the behavior that we see in the F block. All right. So those two D block elements exhibit reactivity and properties that are similar to those elements in the F block, but they're still D block elements. And the final two, lutetium and lawrencium, are 100% F block elements. They do not belong in the D block. So some periodic tables place them up there, but that is incorrect. Now, the periodic table that I provide for you, element. Oh my gosh. That's awesome. Here, let me fix that. Salvage, that is a great catch. There are no elements on the periodic table. Whoops, but there are some elements. There we go. That's my first facepalm moment of the morning. So, anyways, the periodic table that I provide you on the exam places lanthanum and actinum in the D block as they should be, and so if you use the one provided, for example, on the exam 2 when you're doing your electron configurations, you'll be totally solid. But if you see a different periodic table or you use a different one, have one saved to your computer, and you notice that difference and are confused, know that it's lanthanum and actinum have been placed with the other F block elements because they have similar properties, but technically they are D block elements. They do not have any electrons in F orbitals. Yeah, lanthanides are named after lanthanum. Okay, Raj, great question. You'll notice that lanthanides are named after lanthanum, and actinides, which is the second row on the so these are lanthanides. On that top row on the F block, and these are actinides right here. The second row of the F block are called the actinides, named after actinum. The reason why the lanthanides are named after lanthanum is because the chemical properties of the lanthanides and physical properties, chemical reactivity, physical properties, are all very similar to lanthanum. There's very little difference between different members of the F block. They all have a very similar kind of reactivity set, physical properties, etc. So they're all named after lanthanum, which kind of is the first of its kind, or the first of its name, I guess, if we're getting all Game of Thronesy. Same with the actinides, are all very similar to actinum, but lanthanum and actinum are D block elements, whereas the lanthanides and actinides are F block elements. Now, they were named after them based on their physical properties, not their electron configurations, if that makes sense. Totally. So, let's see. So that is the reason why. Totally great questions all around. All right, and actually, I just realized I scribbled all over my periodic table, so I've got to go grab a new one. So pardon this strange interlude. All right. No. Let's see. Okay. Oh, almost. Sorry. Photoshop's being a little... There we go. There we go. Okay. We are back in the business. All right. Okay. Okay, cool beans. Okay, sorry about that. I had to grab a... Oh, hang on one second. All right. Okay. I have my 11-year-old is watching my almost 2-year-old, and she forgot lecture was going on. So they both love loud noises, which is why they get along so well. Okay. Sorry. Now I'm back. We got the lanthanide and actinide question taken care of. The periodic table I provided for you has lanthanum and actinum in the correct spot. Their correct spots on the periodic table. Now we're almost done with Lewis structures. Not Lewis structures, electron configurations. There's one last thing we have to talk about, and then we'll be on our way. And that is, we need to talk about the electron configurations for ions. All right, so how do we write electron configurations for ions? Every single example that we've done up to this moment in time, we've done the electron configuration and orbital diagram for elements. How do you handle ions? So there's 2 steps to do it. First, to do the electron configuration of an ion, you first have to... Whoa, that looks like a multicolored 11. Let's fix that up. All right, so first, you write the electron configuration for just the element. So for the neutral element, and then second step, you add or subtract electrons based on whatever ion that you're doing, right? We know that ions have either lost electrons, so they're positive, or have gained electrons, so they're negative. So you take the regular electron configuration and then add or subtract the ions accordingly. So, oops, sorry about that. Okay, hang on 1 second. Photoshop is... Oh, wait. There we go. There we go. Okay. All right. So let's do an example. Let's write the electron configuration and orbital diagram for oxide. All right, oxygen with a -2 charge. Now, before we can do this for the ion, we first have to do it for the neutral element. So step number 1 is we find oxygen, right? Its nearest noble gas is helium. So we're going to start by putting helium in a bracket, right? And then we look, oxygen is on 1, 2, the second period. You'll notice that starting from the left-hand side of the periodic table, we move through the S block. All right, so this is going to be 2s2. And then starting in the P block, we go 1, 2, 3, 4 spaces in. So this will be 2s2, 2p4. All right, and so that is our electron configuration for oxygen. And oxide, now the only difference between oxygen and oxide is oxide has a charge of -2. That means that we have 2 extra electrons. More than oxygen. So where are those 2 extra electrons going to go? They're going to drop right into our P subshell. So the electron configuration for oxide will be He, 2s2, 2p6. That's the electron configuration. And then the orbital diagram, we've got our 2s subshell, our 2p subshell, and we will have 2 electrons in our 2s and 1, 2, 3, 4, 5, 6 electrons in our 2p subshell. So this is the electron configuration and orbital diagram for oxide. All right, we had a negative ion, so we had to add electrons, 2 more electrons than normal. All right, let's take a look at a positive ion. All right, let's do the electron configuration and orbital diagram for magnesium cation, which has a charge of +2. So first off, we need to take a look at elemental magnesium. Now, magnesium is number 12. That makes its nearest noble gas neon. So our electron configuration, for our electron configuration, we'll use neon as our noble gas abbreviation. Magnesium is down on the third period, and it is 1, 2 spaces in. So the electron configuration for neutral magnesium metal is neon 3s2. All right. Now, when you look at magnesium cation, this means that we have lost 2 electrons, all right? So that means that we have to take 2 electrons out of our highest energy orbital, all right? This means you're going to remove 2 electrons from the orbital with the largest principal quantum number. All right, here for magnesium, there's no question, there's no competition. There's only one orbital we can remove electrons from, and that is the 3s orbital. So the electron configuration for magnesium will just be neon, right? Because it loses these 2 electrons in its 3s orbital. It's fine if you just write neon in brackets, or alternatively, you could write out neon's electron configuration, which is helium 2s2, 2p6. Either of these are fine and correct for the electron configuration. But for the orbital diagram, you'll notice even if you put neon as the answer, for the orbital diagram, you still need to know what the electron configuration for neon is, because the orbital diagram for magnesium 2 plus has 2 electrons in our 2s subshell and 6 electrons in our 2p subshell. So these are the answers. One orbital diagram, there are 2 possible things you could put down for the answer for the electron configuration. You could say it's just all the electrons of neon, or you could write that out. Even if you don't write it out, though, you still need to know the electron configuration for neon, because that is what will allow you to write the orbital diagram for magnesium plus. Cool? All right, now let's do something a little trickier. All right. Let's do this for... How about we do it for nickel 2? Nickel 2 plus. So first, we need to write the electron configuration for nickel as a neutral metal. And then we'll go from there. We'll adjust our electrons accordingly. So we're going to use argon for our noble gas abbreviation. Well, I just said argon, then started writing helium. Next, we look and see that nickel is on the 1, 2, 3, 4th period. So we're going to go 4s, 1, 2. But then we remember that when we cross from the S to the D, that our D subshell will always be 1 energy level lower than our S subshell. So this may be 4s2, 2, but then we're going to go 3D, 1, 2, 3, 4, 5, 6, 7, and 8. All right, 4s2, 3d, 8 will be the electron configuration for neutral nickel metal. Now, what about nickel 2 plus? All right. Now, to get to our iron... Oh, let's see. Sorry. Jesse's got a question. Followed by the orbital diagram works. Yes, neon in brackets followed by the orbital diagram totally works. Yes, you can only... Yeah, Jesse, that is correct. It actually works for both. The one thing to remember, the orbital diagram only includes the valence, which, in other words, highest energy. Electrons. Totally. All right, so now for nickel. So we have our neutral electron configuration, but want to write the electron configuration for nickel 2, which means we need to remove 2 electrons from the highest shell, highest energy shell. And here we have 2 electrons in our 4s orbital. So these are the 2 that we're going to lose. All right, so the electron configuration for nickel 2 will be argon 3d8, and then the orbital diagram just has the 3d subshell, and we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. All right, and that is the orbital diagram and electron configuration for nickel 2. Now, okay. Questions so far? All right. So let's do one more example. All right. Let's do. How about we do? Oops. Let's do europium 3 plus. Actually, well, no, we are going to do this, but I have one more example to do after this. So we'll do 2 more examples. So first off, we're going to start by writing the electron configuration for just europium, which europium is here. Now, this one's tricky, right, because it's in the F block, so we have to keep track of where we are. When we work our way backwards to ceruleum, which is number 58, we remember that portals out to lanthanum, which lands us down on the 1, 2, 3, 4, 5, 6th period. All right, so our europium 63, our nearest noble gas with fewest electrons will be xenon 54. So that is going to start our electron configuration with a xenon core. All right, now we have to count our way through. We count 2 spaces over, 1, 2. So this will be xenon 6s2. But we remember that we are at the 6s, so that means we're filling the 5d. All right, we jump over 1 space, 6s2, 5d1, but now we're jumping down to the F block, which if we're in the 5d, that means now we're dealing with the 4f. All right, so 6s, or here, I'm going to switch colors to yellow. We're dealing with the 4f. 6s2, 5d1, and then we jump 1, 2, 3, 4, 5, 6 spaces over to europium. So this will be 6s2, 5d1, 4f. Let me see, that was 1, 2, 3, 4, 5, 6. 4f6. All right, that is the totally, yes, I think I said 5f. It is 4f. Totally correct. All right, so that is the electron configuration for europium. We have a charge here, though, of positive 3, so we're going to lose 3 electrons from the highest shell. Right? From the highest shell. And you'll notice our highest energy shell only has 2. So we need to snag our 3rd electron from the next highest energy shell, which will be 5d. So the electron configuration for europium 3 will be xenon core. We lose our electrons in our 6s subshell and our 5d subshell. So it'll just be 4f6, which means our orbital diagram, let's see, 1, 2, 3, 4, 5, 6, 7. We've got 7f orbitals, 4f, and 6 electrons. 1, 2, 3, 4, 5, 6. And that's it. So this is the electron configuration for europium-3. All right, now I have one last example to do with you. I'll see if any questions roll in. All right, our final example for ionic electron configurations will be silver 1. Seemingly innocent example. But let's write out the electron configuration for silver first. All right, let's see. Silver is number 47. Its nearest noble gas with fewer electrons is krypton. So that will begin our electron configuration. Now, silver is down on the, let's see, 1, 2, 3, 4, 5th. Well, that looks like an S. 5th period. And remember, we've got to jump into the D block here. So this will be 5S, 1, 2. So we've got 5S2. Then jumping into our 4D, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5S2, 4D, 9. Now, this is not the electron configuration for silver because you'll recall if you write out the orbital diagram, I'm going to make these a little smaller. 5s4d. We've got 2 electrons in our 5s, and we have one, or here, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll remember that when you have, so you can see I've drawn these in different colors. We have 4 electrons in our d orbitals with parallel spins, the down spins here. And whenever you have 4 electrons with parallel spins in a d block, they're going to steal an electron from the s subshell. So this is not the electron configuration or orbital diagram for silver because one of these electrons gets promoted from the s subshell to the d subshell. So the correct orbital diagram for silver looks like this. There's 1 solitary electron in the 5s subshell, followed by 10 electrons in the D. All right. Oops. So this is the correct orbital diagram, which means that the correct electron configuration is 5s1 4d9. All right. So this is the electron configuration and orbital diagram for neutral silver. We need to, for silver cation, right, we have a charge of +1. We need to lose 1 electron from the highest shell, right? And that 1 electron is our electron in our 5s. So the electron configuration for silver cation then, has a krypton core, and it's just 4d10, and our orbital diagram then is just 10 electrons in our 4D subshell. All right, and this is the answer. All right, so that is, again, that's our last example. Just a reminder to keep an eye out. Anytime you have a 9D electron configuration or 4 electrons in your D subshell, you're going to steal one from your S. Oh, I see I made a mistake down here. There we go. Oops. Anytime you have 4 D electrons or 9 D electrons, you're going to steal an electron out of your S subshell, promote it up into the D. Cool. So that brings us to the end of our discussion of electron configurations. The last thing we have to talk about in this chapter before diving into Lewis structures is something called periodic trends. Oop. All right, periodic trends. Okay, here, hang on one sec. Alrighty. So periodic, trends. All right, we've got a few to talk about. The all right, so the first the idea behind a periodic trend is these are properties that that every element on the periodic table has, and they are different for every element, but they change with a general trend that can be tracked as you move across the periodic table. All right, so as you move either from left to right, from up to down, by comparing the relative position of a couple elements on the periodic table, you can assert something about their atomic radius, their ionization energy, electron affinity, etc. All right, so the first that we are going to talk about is something called atomic radius. So these are periodic trends are properties of atoms that vary predictably across the periodic table. All right, and the first of these that we're going to look at is atomic radius. All right, so the atomic radius is defined as the distance. It is the distance. Whoa, I didn't want that in salmon. It's the distance between the nucleus and the valence electrons, which are the electrons that are furthest from the nucleus, right? The electrons in the highest energy shell. So kind of the way to visualize atomic radius is you have the nucleus, right, with the proton, and then you have several shells of electrons. So you may have or I'm not going to get all fancy. This is a very, very poor circle. I had a calculus instructor. I'm actually going to try to do better for you, Fadi Nasser, if you are watching, which you're probably not. But he always said he was horrible at drawing circles, but his circles were amazing, at least to my eyeballs. Okay, that's all the fussing over this I'm going to do. It still looks like garbage. His are still amazing. Anyways. So the atomic radius is defined as the distance, right, between the valence electrons and the nucleus. This R right here. Whoa. Again, if we're assuming that an atom is somewhat spherical in shape, it's this radius from the inside of the sphere to the outside of the sphere is what we're talking about, that distance. And atomic radius is another way to think about this. Is it basically tells you the atom's size. You can think of this as this trend is telling you the atomic size, because essentially, as we'll all remember from geometry, it is the radius of a sphere that determines how large, how much volume it takes up. So the longer the radius, the larger the sphere, the larger the atom. All right, so how does this trend as you move along the periodic table? Well, it'll come as no surprise that the atomic radius increases as you move from top to bottom. All right? That the smallest atomic radius will be higher up on the periodic table, and the largest will be, I shouldn't circle these, it makes them look like charges. The largest will be lower down, and that's just a reflection of the fact that the shell that your valence electrons are occupying are increasing, right, as you move down the periodic table. You start up at the top, and your shell is 1, and then as you move down, it increases, right? We start at 1, 2, 3, 4, 5, 6, 7, etc. So as you move down the periodic table, the size of your atoms are getting larger and larger because the valence electrons are getting further and further from the nucleus. All right, and that is the trend as you move top to bottom. The question is, what happens when you move from side to side? I'm actually going to lasso a little bit here. So we're smaller up here. We're larger down here. But what happens as you move across the periodic table? All right, starting from the left and moving to the right. All right, how does this trend? And you may think that, well, if you look at the atomic numbers as you move across a period, they're getting bigger. So you may be tempted to think like, oh, I bet the atomic radius will increase, all right, as you move from left to right, but it doesn't. It actually decreases. The largest elements will be on the left of the periodic table. The smallest elements will be on the right The question is why? Why does it trend this way? And the answer to that question is as follows. All right, so I want you to compare two elements. Let's compare magnesium. Oh, no, let's compare aluminum and chlorine. All right, aluminum versus chlorine. If you look at aluminum, we can write its electron configuration, no problem. Aluminum has a neon core, right? And then has the electron configuration 3s2, 3p1. Now, when you look at chlorine, it's going to be very similar. Neon core, 3s2, 3p5. Whoa, excuse me. So our electron configurations are the same. When you look at the valence electrons for both aluminum and for chlorine, their valence electrons are on the same shell, n equals 3, which means that they're roughly the same distance from the nucleus, all right? What we have essentially is a tie, because neither of them has a higher energy valence electron than the other. The question is, what is the tiebreaker? They're both on the same shell, roughly the same distance. What breaks this tie? And the answer... Oh, hang on one second. All right. The tiebreaker comes from their proton counts. If you look, aluminum has how many protons in its nucleus? 13 protons. Chlorine has 17 protons in its nucleus. Now, even though they're on the same, their valence electrons are in the same shell, the 17 electrons in chlorine's nucleus, because it has more electrons, they pull harder on the valence electrons than aluminum's can, right? Because the attraction that the electrons in chlorine's valence have to the 17 protons in chlorine's nucleus is stronger than the attraction of aluminum's valence electrons to its 13. So these so more protons, the greater number of protons in chlorine's nucleus pull harder on the valence electrons, causing it to be slightly smaller. So more protons pull harder on the valence electrons, and this makes chlorine have a smaller atomic radius. All right? So when you are looking at two atoms, whichever one is lower on the periodic table will automatically be larger because those valence electrons are in a higher energy orbital. Yeah, exactly. It's like aluminum has 4 less protons than chlorine does. But when two elements are on the same period, all right, they both have their valence electrons in the same shell. The tiebreaker is going to be whoever has more protons. All right. So if I were to ask you to compare, right? So if I were to ask you, which atom is larger, all right, and I were to pick two, so if I were to pick let's say, why not? How about magnesium versus strontium? All right. You find them on the periodic table. Magnesium, strontium. Strontium is down on the 5th period. Magnesium is on the 6th. So strontium is larger because its electrons are in a higher energy valence. All right. If I were to ask you to find another one, like let's say I were to ask you to tell me which one's bigger, germanium versus selenium. All right, first we have to find them. Right, they're kind of weird, but germanium's right here, selenium's right here. Now you'll notice that they're both 4th period elements, but because germanium has 32 protons in its nucleus, selenium has 34, because it has more protons, the greater positive charge in the nucleus pulls harder on the valence electrons, causing them to shrink a little bit, to contract. It pulls them in. Whoa, I circled the smaller one. Selenium is not larger. Selenium is smaller than germanium. My bad. Yeah. Now, third and final. Whoa. If I were to ask which is larger, chromium. Whoa, what happened there? Something happened with my brush size. There we go. If I were to ask you what's bigger, chromium or silver. All right, again, first we find them on the periodic table. There's chromium, here's silver. Now, again, this one's, I'm trying to trick you with this one because silver's further to the right than chromium, so I'm trying to get you to use the exception, not the rule. All right, the first thing you look at is where are the valence electrons? All right, chromiums are on the 4th shell, silver are on the 5th shell. Because silver's electrons are on a higher shell, it is bigger every time. It doesn't matter that it's further to the right. That is only your tiebreaker. Whichever one is lower on the periodic table will always be larger. If they're on the same period, same row, then that is what breaks your tie when it comes to atomic radius. Cool? Let's look at another periodic trend. Let's look at ionization energy. Whoa. There we go. So ionization energy. Ionization energy, the definition of ionization energy is it is the delta H for the following reaction. It's the delta H for the reaction where you take a neutral element and you ionize it. You rip an electron away. So you create a positive ion plus a free electron. So essentially it's asking how easy is it to pull an electron away from an element, all right? And the lower the energy is, the easier it is to steal an electron. The higher the energy is, the harder it is to steal an electron. And this trend tracks with electronegativity. So, for example, if you were to compare, if you were to compare potassium versus bromine. All right. Finding these two on the periodic table, potassium's here, bromine is here. All right. Potassium, you'll notice, is actually, I'm going to change bromine's color to blue. So you'll notice potassium is what has one more electron than argon, right? If it loses one electron, it gets argon's electron configuration. That's something it wants. If you look at bromine, bromine is one electron away from its noble gas as well, but it needs to gain one more electron, all right? So bromine wants to gain electrons, potassium wants to lose them. And so it's going to be a lot easier to steal an electron from potassium than it is from bromine. So we can expect potassium to have a low ionization energy. We can expect bromine to have a high ionization energy. All right? Because of their relative place on the periodic table. So ionization energy increases as you move from the left side of the periodic table to the right. All right? As you move from left to right, your ionization energy increases. All right. Now, how does ionization energy change as you move from top to bottom, or bottom to top, as the case may be? Now, your ionization energy when you're moving from the bottom to the top of the periodic table goes like this. So, if you compare, for example, let's compare cesium to lithium. All right. Let's go lithium versus cesium. So lithium if you consider the ionization energy for these two, lithium has a smaller atomic radius. Cesium has a large radius. All right. So we've got a large radius on cesium, a small radius on lithium. Because cesium has a large radius, that means the electrons are farther away. They're farther from the nucleus, which makes them easier to steal. All right, they're easier to take. Whereas lithium, its valence electrons are closer to the nucleus, which makes them harder to take. So those of you with physics in your background will remember that Coulomb's law, right? The strength of the attractive force between charges is inversely proportional to the radius squared, right? So the smaller the radius, the larger that attraction is. The larger the radius, the smaller that attraction is. So the lower down on the periodic table you are, the lower your ionization energy will be. The higher on the periodic table you are, the larger your ionization energy will be. So left to right, it's increasing. Bottom to top, it's increasing. And that is ionization energy. Okay. Sorry, Vraj, I see I missed a question from you. You said, what about the ones in the F block? Are you asking about So quick question. Are you asking about atomic radius or ionization energy? Is my question for you. Atomic radius. Okay. Great question. So let's do F block AR. All right, F block atomic radius. So if I asked you which is larger? And for my first example, let's say I'm asking you to compare samarium versus zirconium. All right, now zirconium is right here, which puts it on the 1, 2, 3, 4, 5th period. All right. Now let's look at where samarium is. How do we know whether this one's bigger or smaller? Well, when we go all the way to ceruleum, that ports us out here and takes us all the way to the 6th period. So samarium, actually I'm going to array this slightly differently. I'm going to go samarium versus zirconium. All right. If you look at the electron configuration for zirconium, it's krypton 5s2 4d2. And if you look at the electron configuration for samarium, it's xenon 6s2 5d1 4f5. All right. So when we're talking about atomic radius, whichever one has valence electrons in a higher shell will have a larger radius. And you'll notice that samarium has electrons in the 6th shell, whereas zirconium only has electrons in the 5th shell. So that makes samarium larger. So what you have to do when you're comparing these two is look at, just like anything else, the relative position on the periodic table, but you have to remember what period your F block element is falling into. All right. Okay, so I see your question. What about radium and cerium? Okay, so I think I've been calling it ceruleum. That is dumb of me. All right, let's see. So let's take a look at radium, which is Ra, versus Ce. All right, so radium is here. It is down 1, 2, 3, 4, 5, 6, 7. Right, so radium's nearest noble gas is radon, and then it is 2 spaces into the 7s block, so 7s2. Now Ce, cerium, ceruleum. Okay, I'm super embarrassed. Ce is right here, right? Which to find its period, we got to remember that it bumps in on the 6th period, right? So its nearest noble gas with fewer electrons is xenon. This would be 6s2. Oops, not 3d. 5d1, 4f1. So radon has electrons on the 7th shell. Cerium only has electrons on the 6th shell, which would make radon larger. So really, all you have to do with the F block elements is remember what period they belong to. And the key to that is remembering that they port over right here after that first space in the D block. Cool. So that is how you handle. Yeah. Let's see. Radium is larger than thorium. All right. Well, first we've got to find thorium, which, to be honest, I don't. There we go. TH. Thorium, which is 90. So if we go Ra versus TH, we already know where radium is. Now we got to find thorium, which is right here. Ah, okay, great. So thorium ports in here. Actually, I'm going to do the exact same thing, but I got to arrange them differently. So if we go radium, which we already have our electron configuration, 7s2, and then thorium, which also has a radon core, 7s2, 6d1, 5f1. There we go. So you'll notice that they both have electrons on the 7th period, right? So essentially they're the same size. But what we have to do then is look to our tiebreaker. Which one is further to the right? And because atomic radius decreases as you move from left to right, so it's smaller, further to the right, it's larger, further to the left. Radon is further to the left than thorium, which also makes it larger by the tiebreaker. It's larger because thorium has more protons in its nucleus. They're on the same period, but thorium has more protons. So that makes thorium smaller and radium larger. That is correct. Totally. All right. So the last periodic trend that we're going to talk about today is so here, hang on, actually. So hopefully that answers your questions. So atomic radius is related to electronegativity. Only when you're moving horizontally across a period. Oh, no, Raj, don't apologize for questions. They're the lifeblood of any course is student engagement. So electronegativity. So here, actually, just as a quick review. Whoa. Thank goodness for the lasso tool. So electronegativity. There we go. Oh. So electronegativity increases as you move from left to right. All right, so the closer you get to the right-hand side, the more elements want electrons. And it increases as you move from bottom to top. And this is the difference between electronegativity and atomic radius. Is as you move from the bottom of the periodic table to the top, your electronegativity increases. But that is the opposite for atomic radius. As you move from bottom to top, atomic radius shrinks. So that's the key difference in between electronegativity and atomic radius. Though you can see that ionization energy tracks with electronegativity. It's the same. And our last periodic trend, which is called Electron Affinity, also tracks with electronegativity. All right, so Electron Affinity, which is almost the opposite of ionization energy. Electron Affinity, ionization energy is the delta H for turning something into a cation. Electron Affinity is the delta H for turning something into an anion. How bad does an element want to become an anion? All right, it is the delta H for this reaction. And the electron affinity tracks with electronegativity. It increases as you move from left to right. And it also increases as you move from bottom to top. Your electron affinity is greater the higher you are on the periodic table, and it's greater the further to the right you are. Yeah, exactly, Raj. Atomic radius is the odd one out. Which is far and away my preferred YouTuber that my kids watch. Or is it the odd ones out, not Atomic Radius? I don't know if that's a YouTuber. Probably is. Cool. So that sums things up for periodic trends. All right. Oh, here. I actually can now zero out our periodic table because we're done with periodic trends. We've covered electron configurations in their totality. And now we're ready for something new. We're actually ready to start getting into what I have written up here, an intro to Lewis structures. All right, now a Lewis structure. So we're going to start with a Lewis dot structure. And all this is it is a different way to write the same thing that we've been writing, to communicate the information we've been communicating through electron configurations and orbital diagrams. All right. So the idea behind a Lewis dot structure is it's just another way of saying the same thing. All right. Different names for the same thing. So, for example, the difference is I guess before getting to the example is a Lewis dot structure communicates information about the electronic structure of an atom using Whoa. Photoshop's getting tired. Using the elemental symbol and dots. All right. And these dots represent electrons. All right. So, for example, if you looked at carbon, for example, we could Oh, let's see. Do I want to do carbon? Sure, why not? We could look at the electron configuration for carbon. It's got a helium core, an electron configuration of 2s2, 2p2. All right. So the dot structure is only concerned with the valence electrons. All right. Just like with the orbital diagram, we only looked at the valence electrons. When we're talking about a Lewis dot structure, we are only interested in the valence electrons around carbon. And you'll notice that we have 4 valence electrons to place. So our Lewis dot structure for carbon will have 4. Now, the way that you write the Lewis dot structure is you start by writing the elemental symbol. And visually, the way you visualize a Lewis dot structure is there are 1, 2, 3, 4 sides. All right. There's 1, 2, 3, 4 sides. And you're going to place 1 electron on each side as you, 1 valence electron and on each side, and you're going to rotate around. So we place our first electron on side number 1. The second electron goes on side number 2. The third electron on side 3. The fourth electron on side 4. So the Lewis dot structure for carbon is simply going to look like this. 1, 2, 3, 4. But you kind of visualize a box around the elemental symbol and then place 1 electron on each side, and you kind of move around like so. So that is the Lewis dot structure for carbon. All right, let's do a few more examples. Let's do nitrogen. All right, nitrogen. Now, actually, you know what I'm going to do? Excuse me. I'm going to bring our periodic table back. All right, because you may be thinking, okay, do I need to write the electron configuration every time I want to draw a Lewis dot structure? And the answer is no. You can actually get the Lewis dot structure from straight off of the periodic table. Now, when you look at it, all right, all you have to do is find nitrogen on a period. All right, and nitrogen's right here. And you'll notice that it is 1, 2, 3, 4, 5 spaces over. So nitrogen has 5 valence electrons. All right. However many spaces you are into the main group, that's how many valence electrons you have. And so to draw the Lewis dot structure for nitrogen, okay, again, remember, we treat each side, we treat the elemental symbol like it's a box. 4 sides. So we're going to place all 5 valence electrons. 1, 2, 3, 4. Now we have 5 valence electrons to place, but we put 1 electron on each side. So one of our sides has to double up, 2. So the Lewis dot structure for nitrogen simply looks like this. All right. You can have a maximum of 2 electrons on a side because you can have 2 electrons in an orbital. That's why that follows that case. Now, if you're wondering why are there 4 orbitals, because in the main group we have 1s plus 3p orbitals. So that's 4 orbitals total. That kind of got smushed. No, it's getting smushed again. Oh, well. All right, so that is the electron configuration for nitrogen. Let's do another one. Let's do oxygen. All right, now oxygen is 1, 2, 3, 4, 5, 6 spaces in. All right, so the electron configuration for oxygen, the electron configuration for oxygen is helium core, 2s2, 2p4, which means that we have here 6 valence electrons to place. So oxygen will have a Lewis dot structure with 1, 2, 3, 4, 5, 6. All right. Let's do one below. Let's do sulfur. Sulfur, you'll notice, is right underneath oxygen, which means it has the same number of valence electrons. All right. So, and if you look at the electron configuration, it's neon 3s2, 3p4. All right. So sulfur has 6 valence electrons like oxygen. So it'll have 1, 2, 3, 4, 5, 6. There's the electron configuration for oxygen and sulfur. And I'm not doing electron configurations. I'm doing Lewis dot structures. Sorry. Tripping all over the place. Now, not finally, but let's do selenium. Se. Now with this one, you might be going, wait a minute. I said earlier that every element in the same column will have the same electron configuration and, same Lewis dot structure. But if you look at the electron configuration for selenium, it has an argon core. It'll have the electron configuration 4s2, 3d10, 4p4. Now, you may be going, whoa, there's a lot more electrons in this electron configuration. Does that mean we have a bunch more in our Lewis dot structure? And the answer is no. The answer is no, because you'll notice that we only have 2 subshells in our highest energy shell in selenium, right? We only have the electrons in the S, 4s, and 4p, all right? The electrons in the D subshell are in the 3rd shell, and so they do not count towards our valence electron count for our Lewis dot structure. So we still only have 6 electrons, which means the Lewis dot structure for selenium will have 1, 2, 3, 4, 5, and 6. All right. So everything in column 6, every element will have 6 dots in its Lewis dot structure. Just like everything in column 5 will have 5, 4 will have 4, 7 will have 7, etc. All right. Now, if your question is, at this point, what about the D block or F block? All right, if that is your question, the answer to your question is do not worry. Turns out Lewis theory does an amazing job of explaining the bonding and reactivity we see for main group elements. But it breaks down, it does not account for the bonding and reactivity we see for D block and F block elements. So what we're learning now with Lewis dot structures, and then Lewis structures a little bit later, it only applies to main group elements, which is the F block, which is the S block and the P block. All right, together. So you will never have to draw Lewis dot structure for a D block element or an F block element. We're only going to be working with the main group for this stuff. Cool? Okay. Oh, all right. We're going to call it a day there. I am so sorry. I've been out of it. So I was looking at the clock, watching the clock the whole time, and it's 10 past 1. In my brain, I thought we were going to 1:30, but I should have ended 10 minutes ago. I apologize for that. We will pick up with our discussion of Lewis theory on Wednesday. So this is all the official. This is the end of official lecture. But before I go, I apologize for running late. Spring break, I forgot. Or that's my excuse I'm using. I forgot how long our class actually runs. Before I go, let me ask any questions, comments, things you want to talk about. I'm down to hang out and kick it for a little bit. I know some of you have already left because you have to get to your next class. I apologize for running over. But those of you who are still here, I don't know if you have any things you want to talk about, any of the business questions, other questions. We can talk about one-wheeling, or what we've been watching. Whatever, I'm down to hang. If you guys are down to hang. My apologies for running over with today's lecture stream. So we just barely got into Lewis structures, and we will continue that discussion on Wednesday. It was really nice to see everybody, actually. I missed all your gleaming faces and YouTube handles. Oh, we dropped down to 12. No, 11. Dropping like flies. An OChem question. So I can, is that okay? It is okay. If you ask in an OChem stream. OChem office hours are Monday and Wednesday at 6:30 p.m. If you can't log in at that time, you can always email your question with Chem 420 office hours as the subject line. And I will totally answer it, and so you can log in, check out the stream at that moment, at that point in time, and get an answer. I don't want to answer it, Raj. The reason why I don't want to answer it here is because I'm kind of trying to keep the Gen Chem and OChem content separate, just because OChem can benefit all my OChem students, but they're not going to go looking in a Gen Chem feed to find OChem answers. Does that make sense? So I'm totally down to answer your question just during an OChem stream. That way it kind of keeps everything, and I will totally answer it. That way you can go back and as always, in the comment section, I catalog the video with time signatures, so you'll be able to click right to the answer and see it. Totally. So I'm 100% down to answer your OChem questions. I just I want to do it in an OChem stream. Totally. Scrolling through the comments, Raj, it's been you and I for kind of a while. But let's see. We saw Jesse Salvesh early on, where people were poking up their heads. Yeah, I hope your guys' spring break was better than mine. Although I'm imagine that there was a lot of sheltering in place going on, which can only get so exciting. Yeah, totally. I mean, I'm totally down to talk about anything. Okay, let's see. What is the electrical connection? Oh, interesting. Okay, the electrical connection between potassium and sodium related to neuron action potential. All right. Now, I don't know a ton about neuron action potential, but one thing I can point out from a chemical point of view. So if you look, and actually, I'm going to pull up the periodic table. So let's take a look at potassium and sodium. And they are kissing cousins. They're right here, same column on the periodic table. All right. And one of the things you'll notice is they have very similar electron configurations. Sodium, does not have an argon core. It has a neon core. And actually, in the body, they do not exist as sodium or potassium atoms. They exist as ions. So sodium plus actually is just a neon core. And potassium cation is just an argon core. So we can further expound here. 2s2, 2p6, and then potassium 3s2, 3p6. So when you look at them, they have the same charge. Really, the biggest difference between these two is when you look at the valence electrons, you can see that potassium has valence electrons on the third period, and sodium has valence electrons on the second period. So potassium is a larger ion. And sodium is a smaller ion. And so when you think about how these different things are reacting in the body, yes, totally, that's my bad. Potassium should be neon. It's a complete argon or neon core 3s to 3p6. Yes, totally. Totally, great catch. Total. I meant totally. Yeah. So potassium's a larger ion, sodium's a smaller ion. So there are some membranes, proteins that can bind sodium, or sodium can pass through because it fits through a smaller space that potassium can't. And so that definitely has some difference in their behavior in solution. Again, I don't know a ton about neuron action potential, but from what little I remember, I believe the most significant difference between these two in the biological system has to do with their size, which, interestingly enough, boils down to atomic radius, which we actually talked about today, which is kind of cool. So that's fun. Gen Chem can be applicable. Other questions? Things? Oh yeah, of course, Raj. Of course, my pleasure. My favorite thing is being useful. I don't know if that's because I have low self-esteem or what, but if I can be useful, then I feel like why not live one more day? No, what am I saying? I've got a kid. That's gonna keep me living for at least another 18 years. All right. Let's see here. I'm actually logging in to see how many people have responded to, the feedback quiz so far. I'm kind of interested in seeing feedback. Wow, actually. 4, 5, 6, 7, 8. $26. So about half of you guys have actually responded, which is awesome. I don't know if everybody else just doesn't care or what, but no, it's you all have till Friday, right? But 50% response rate is totally rad. And again, I'm very, very much interested in knowing what you guys think. So I think the feed is kind of it's kind of drying up a little bit. So with that being said, I just want to say, remember, we're back with a vengeance this week. Everything is up and running. I just want to do a plug for office hours. That's not how you spell hour. Office hours are this Friday. From 1 or at 1:30. No, just at 1. So email your questions. You can also ask them live, but if you send in an email, if this time doesn't work for you, you can still get your questions answered. You need to do 2 things. First, you need the subject. Chem 400 office hours. That way I can find your email. And then the second thing you need is so please attach a picture of the problem. That way it will keep everything more streamlined and allow for a smoother stream. Yeah, totally. So anyways, it was great seeing everyone. I actually missed you all a ton. I'm glad we're back in the swing of things. And yeah, we're going to keep rocking till the end of the semester. I'll see you all on Wednesday, and then hopefully some of you Friday. Later.